Awesome. Uh, so, hello everyone, and uh, welcome to this month's Grundfest Memorial Lecture. My name is Pradyumna, and I'm very glad to see you here. I'm sure, like a lot of us were at CPR, and we must be very tired. So it's really great to see such a huge turnout this week as well. So, before I hand over the mic to this month's speaker, Alankar, I'll just give a quick introduction to the lecture series itself. So before that, as usual, our lectures typically start at 12:05 just to allow people to trickle in. And the talk will go on till 12:50, uh, followed by questions. Uh, and please do follow our lecture series webpage in case you'd like to stay updated with our future speakers as well, since we have a bunch of very exciting talks lined up in the next few months. So the Grundfest Memorial Lecture Series is named after Professor Warren Grundfest at UCLA. He was an SPIE Fellow in Biophotonics and a pioneer in many imaging modalities. However, of most relevance to this lecture series is that he was a great advocate of junior scholars, which is also the principal focus of this lecture series. Uh, at this stage, I'd also like to express my sincere thanks to my co-organizers, Professor Achyuta Kadambi and Professor Katie Bowman, who've really done all the heavy lifting at the back end to ensure that we have our speakers and the entire thing is sort of scheduled. I'd also like to thank Ellen Zhao, uh, a first-year PhD student at UCLA, who also helps a lot with organizing the lecture series and who will be taking over co-organizing from next cycle onwards. Finally, we'd also like to thank our sponsor, Akasha Imaging, which is a computational imaging startup on polarization, for graciously sponsoring an inverse honorarium for non-permanent speakers, which means they sponsor a small amount of money as gratitude to our non-permanent speakers, like PhDs and postdocs, for taking the time to describe their amazing work at this forum. So with all that being said, it's my great honor to introduce our speaker for today, Alankar Kotwal, who's a PhD candidate at Carnegie Mellon University. Alankar today will be talking to us about his amazing work in computational interferometry. So without any further ado, I'll stop sharing my screen now and hand over the mic to Alankar.
All right. So thank you so much for that introduction, Pradyumna. So hello, everyone. I'm Alankar. I'm a PhD student at Carnegie Mellon University, working with Professor Yanis Kulikas and Professor Anath Levin at the Technion. I'm going to talk about my PhD thesis work on computational interferometry. Oh, go ahead. All right. My research is driven by two major thrusts. Firstly, it's part of an inter-university collaboration that works on optical soft tissue imaging. Just like X-ray CT revolutionized the 3D reconstruction of the internal structure of the human body using X-ray projections, this collaboration aims to computationally reconstruct the structure of soft tissue using optical measurements taken under a variety of illumination and imaging settings. For example, this figure on the left shows the soft tissue structure of a healthy and cancerous tendon that's biopsied and imaged through a microscope. We want to be able to perform the same kind of imaging non-invasively. The ability to image soft tissue in this way paves the way for applications such as optical biopsies and high-resolution wearable imaging devices. However, this is a difficult problem. Unlike X-rays, which travel straight through tissue and only get attenuated, light scatters strongly when it interacts with tissue and traces out complex paths between the light source and the camera. This effectively blurs the tissue structure in images that are taken by an ordinary camera, as we can easily see upon holding a flashlight against our hand. In order to reconstruct the tissue, we need to invert the scattering. Tissue structures are typically of the order of microns. For example, the smallest capillaries are around 10 microns in diameter. Thus, any kind of imaging that is to invert this scattering needs the capability to separate light paths at micron resolutions. The imaging modality that we use is a classic wave optics technique called interferometry. Our second research thrust is developing a general theory of interferometric imaging from first principles of Fourier optics under user-specified illumination conditions. We can further try to match the predictions from this theory to actual interferometric measurements in order to estimate soft tissue structure. Beyond soft tissue imaging, the techniques that we develop have vital applications in inspections of manufactured parts to see if they meet their specifications to micron accuracies. For example, here, the shape of a smartphone camera lens. These measurement capabilities can be used further for feedback during manufacturing. There is work at CMU on 3D printing soft biomaterials to graft onto hard tissue, to which our methods have significant relevance. While interacting with micron-scale structures, light behaves like a wave. This renders most ray optics models of image formation and most traditional computer vision inaccurate. The brilliant colors that are formed by thin film interference in oil films and tracks on compact discs are an example of these so-called coherent effects. These effects are caused by micron-scale thickness variations in the oil film and the micron-scale track structure of the compact disc. Then, if we can bring out these coherent effects from the sample that we are interested in imaging, we can potentially measure micrometer scale structures. As an example, here's a result from later in the presentation, where the sample that we use is carving on the lid of a wooden music box. This animation shows the variation in the response of the scene upon moving a mirror in our optical setup by less than a micron. The response consists of a high-frequency pseudo-random pattern that's called speckle. And even though speckle may appear like noise, it has a definite predictable structure. We can exploit this structure to perform many kinds of imaging, such as, in this case, micron-resolution depth sensing. In this talk, I will first introduce interferometry, define computational interferometry, and discuss some existing techniques that lie within its framework. Then, I will discuss two special cases of computational interferometry that we developed in my thesis: direct-only light path imaging and fast micron-scale 3D shape acquisition. Lastly, I will showcase an interferometric system that enables passive time-of-flight imaging using only sunlight as a light source in the face of challenges such as vibrations, wind, and strong ambient light that are typically fatal to interferometry. Let us first talk about interferometry. Interferometry refers to techniques that measure the superposition of two or more light waves. We use a full-field Michelson interferometer in which we collimate light from a point single frequency emitter, such as a laser diode, split the resulting beam into two parts, one that goes into the scene arm and another that goes to the reference arm. The reference arm is typically a planar mirror that's placed on a translation stage so that it can change its distance to the beam splitter. Upon reflection from these arms, these beams get combined at the camera. The term full field in the full field Michelson interferometer refers to the fact that we illuminate and image the entire spatial extent of the scene together. Now, let's consider a simple case where the scene is just another mirror. When we expose just the scene, we expect to see a flat image on the camera. Similarly, when we expose just the reference, we expect to see another flat image. Both of these are images of mirrors. When both the arms are exposed, in addition to the combination of the two images, we also get an extra interference component. Our signal lies in this component. Interference is an example of the coherent effects that we mentioned before. It is typically a very rapidly changing function of the scene, giving interferometric measurements exquisite micron-scale resolution. Interferometry, therefore, has been used for applications where extremely precise measurements have to be made, ranging from verifying the shapes of optics to detecting gravitational waves. Let's study this interference component. Consider the camera pixel that images the blue point on the scene mirror. The blue point is positioned at a distance d from the beam splitter. As the reference mirror is scanned in position x, the interference component varies sinusoidally. The period of this sinusoid is the optical wavelength that we use for the illumination. When d and x are the same, constructive interference happens. The light waves that are arriving from the reference arm and the scene arm add up in phase. Similarly, When D and X differ by half a wavelength, destructive interference happens and the arms cancel out each other. In a physical implementation of this schematic, it is very hard to align the two mirrors at wavelength scales. Even a slight tilt of one of the mirrors with respect to other introduces a spatial variation in the distance to the scene, causing the interference to appear as spatially varying sinusoidal patterns that we are familiar with as interference fringes. So, how do you use this for measuring surface accuracy? You place an accurately manufactured shape on the reference arm and the test shape on the scene arm. Ideally, if the two match, we should see constructive interference throughout the image. However, mismatches in shape cause fringes that can be used to quantify surface accuracy. Here's a fun fact. How did they detect gravitational waves recently? Using an interferometer. A gravitational wave that's propagating along the scene arm has the property that it induces, without moving the scene mirror or changing D, a path length shift in the scene arm with respect to the reference arm. Using mathematical models of how this path length changes, we can look in the interference component for changes of a similar nature. Back in my thesis, we introduced a set of new interferometric techniques collectively called computational interferometry. Computational interferometry allows precise micron-scale structure on the set of light paths in the interference in the scene of interest. These light paths are specified in terms of their endpoints and path lengths. We achieve this control by modifying the light source used in the full-field Michelson interferometer, both in spatial amplitude profile and spectrum, and sensing in terms of the configuration of the reference arm. One existing special case of computational interferometry is called time-domain optical coherence tomography. Here, instead of using a monochromatic emitter, we use a broadband emitter. Due to this change, as the reference mirror is scanned, the interference pattern is no longer sinusoidal as it was in the case when our emitter was monochromatic. It is sharply peaked when the distances to the scene point and the reference mirror are equal. Time domain refers to the fact that we scan the reference mirror, changing the time of light in the reference arm. Then, if we place a sample, such as a retina, on the scene arm and scan the reference arm, we measure interference signal from deeper and deeper inside the sample, effectively imaging its internal 3D structure. Note that most commercial implementations of OCT are neither full field nor time domain, which is a point that we will discuss later in the talk. However, using the full field setup is vital in computational interferometry and additionally gives us a significant boost in spatial resolution, as we will see later. Now, we can also stack the interference signal at the different reference mirror positions as a video to display the propagation of light in the scene. Here, I will show you an example on a toy cup, which is shown in the top left. As we play this video, we observe light paths of increasing lengths. First, direct reflections from the sides, then direct reflections from the bottom, and after these direct light paths come the so-called global illumination light paths caused by multiple bounces inside the scene. The direct light paths have lengths that are equal to the depth of the scene point that they are reflected from. We can use this property to estimate a depth map of the scene by locating the peak of the interference signal caused by these direct light paths. In the top left, I show a depth map estimated for this cup using OCT. However, in estimating this depth, the global light path, the global light illumination light paths are problematic. Let us now examine a computational interferometry technique that's complementary to OCT, that images only the direct light paths robust to global illumination. We refer to this as direct-only imaging. Let us see a quick example of what direct-only imaging can be useful for. Consider a scattering medium, such as tissue, that's occluding a pattern that's printed on a plane that simulates a slice through soft tissue. Let us examine the camera pixel that's represented by the white box. The light path that creates a sharp image of the pattern at the camera pixel is this green one that traverses the scattering medium unaffected. Note that this is the direct light path. However, there also exist other light paths, such as the ones that scatter multiply inside the scattering medium and end up in the pixel, and those that backscatter, never reaching the pattern. As a result, the image that's captured by an ordinary camera is blurred to the point that the pattern is barely recognizable. Direct-only imaging allows us to optically remove from the interference component the contributions of these multiply scattered and backscattered light paths and perform imaging as if the scattering medium were not present. Then, we capture an image of the setup where the pattern is visible again without the need for any computational post-processing. In this case, the pattern is two white vertical strips on a black background. Implementing direct-only imaging requires just one small change in the interferometer, replacing the point emitter in the focal plane of the collimating lens by an area light emitter, such as an LED. The light beam is now a collection of waves traveling at a narrow set of directions along the optical axis in the interferometer. Let's keep this point in mind for later. I'll now give you a more dramatic example of direct-only imaging. Consider a scene containing a glass bead with mostly reflective facets between two diffuse walls that is illuminated and emerged from the left. The set of light paths in this scene include direct light paths, retroreflective paths, as well as caustics that are created by the interreflections between the bead and the diffuse wall. We can use our direct-only imaging technique to isolate only the direct green light paths by scanning a large constant source in the focal plane of the collimating lens. The rest of the scene image contains the global-only component, including the interreflections and the caustics. We can perform the same operation on the toy cup. Due to the translucent nature of the cup, most of the cup's appearance arises from subsurface scattering, which shows up in the global light path image. Direct-only imaging is only a special case of the general kinds of imaging that we can perform. In the most general case, we use an area light source with a controllable amplitude profile and a phase-modulated copy on the reference arm. We can derive a theory of interferometric imaging from first principles of Fourier optics in the framework of computational light transport. We model the scene as a linear system where light paths are grouped by the endpoints, and the contributions of these groups are added up to form the camera image. And depending on the spatial amplitude and phase profiles used for the light source, we can mask light path groups from the interference component, depending on the relationship between their endpoints. This mask is called a probing matrix, and the system shown here can implement general two-plit probing matrix. There are more details on the theoretical details of the derivation in our paper. Focal planes of lenses in a 3D world are two-dimensional, so we can use arbitrary two-dimensional emitter amplitude profiles. In fact, for the previous seeing through scattering result, we had used a horizontal area emitter. This sharpened the white vertical edges by eliminating any light that traveled horizontally in the scene. Imaging with a vertical emitter emphasizes the black horizontal edges by eliminating any light that travels vertically in the scene. Effectively, we perform optical matched filtering. Then, using a directional light source allows us to select light paths based on the directional relationship between their endpoints, as shown by the diagonal light sources here. Here's a picture of the prototype that we implemented to perform the most general kind of computational interferometer. The blue box is where the area light source resides, and the green box is the general reference arm configuration. We will cover some engineering aspects of this setup later in the talk. Let us now examine an application of direct-only imaging to fast micron-scale depth sensing. First, let's revisit depth estimation with direct-only time domain OCT. Remember that to detect any interference signal from a scene point that's at a distance d, we need to place the reference arm at a distance d as well. Then, to measure an entire scene with depth range L at resolution delta L, we need L over delta L measurements. For a scene that's 1 millimeter in depth range, such as the music box lid that we saw before, this implies taking 1,000 full field measurements. As we mentioned before, OCT systems are typically neither full field nor time domain. Most commercially available OCT systems are based on fiber optics. The structure of a fiber interferometer is exactly analogous to the full field interferometers that we have been studying. Fiber interferometers perform direct-only imaging by illuminating and imaging just one scene point at a time. However, this comes at the price of scanning this imaged point across the scene between exposures. This couples the field of view and spatial resolution. For equal acquisition times, we need to cut down field of view to increase spatial resolution, and vice versa. As opposed to this, our full field setup eliminates the scan over the scene while performing direct-only imaging within exposure. Therefore, theoretically, our spatial resolution can be as high as individual pixel sizes while maintaining sensor-sized field of views. Using full field interferometry, I will now show you a computational interferometric micron-scale depth sensing system that greatly reduces the scan time of time domain OCT and captures depth using a constant number of measurements. Our system uses a procedure called synthetic wavelength interferometry. Instead of the broadband light source that we used in OCT, here we use a combination of two single frequency lasers at slightly different wavelengths. As before, we create from these lasers an area light source in the focal plane of a collimating lens for direct-only imaging. Let us now examine the interference component at the camera pixel that images the blue point on the scene. This point is at a distance d to the beam splitter. When just one of the two lasers is on, as before, the interference component tracks a sinusoid with the same wavelength as the laser with constructive interference at d equal to x. The signal most of the signal comes from the direct light path because of the assumption of direct-only imaging. This assumption means that the overwhelming majority of light paths in the interference component are these direct light paths. Similarly, when just the other laser is on, the interference component tracks a sinusoid with a different wavelength, the wavelength of the second laser, which is also peaked at d equal to x. When both these lasers are on, the interference tracks the superposition of the above two sinusoids. This sum has an envelope, which is shown by the green curve that is another sinusoid, with a long synthetic wavelength that depends on the separation between the wavelengths of the two lasers. Note that even though in this figure I have shown the laser and synthetic wavelengths to be comparable to each other, the laser wavelengths are typically orders of magnitude smaller than the synthetic wavelengths. We are interested in this envelope. Note that the envelope is also peaked when d and x are equal, and therefore estimating the phase of this envelope is enough to estimate d up to a multiple of the synthetic wavelength. Our task is then to estimate the phase of the synthetic wavelength sinusoid at each pixel. We do this using the 4-bucket phase retrieval algorithm. This phase measurement can be performed from the interference component in as little as 16 measurements. Synthetic wavelength interferometry can easily be integrated into a time domain OCT setup by inserting a switch between the broadband light source and the combination of the two lasers. This allows us to compare depths that are captured by both for the exact same scene. In the results that I am about to show you, we perform exactly this, except the synthetic wavelength interferometry results are typically tens to hundreds of times faster than OCT results for equivalent depth resolution. Let's look at some depth reconstructions captured using synthetic wavelength interferometry. The scenes that I am showing you have depth ranges of the orders of millimeters. The wavelength separation required to measure these depths at 780 nanometers is of the order of a nanometer. The second column is the reference depth that's captured with full field OCT, and the third column is the depth captured with our setup. The Harvard logo result highlights the spatial resolution that the full field nature of our measurement provides. To visualize this better, let's look at the synthetic wavelength interferometry depth rendered as a surface, where we can see that the letters on the Harvard logo are reconstructed with high spatial resolution. Here are some results with especially strong global illumination caused by subsurface scattering, such as engraving on soap, engraving on wood, and a bar of Lindt chocolate. Depth reconstruction completely fails in the last column, which has no direct-only imaging. Therefore, we conclude that direct-only imaging is critical in the presence of global illumination. To really emphasize the capabilities of synthetic wavelength interferometry, we will reconstruct the eagle on a United States $20 bill. The features on the bill are raised about 10 microns off of the surface of the bill. And here's the recovered depth. Note how in the recovered depth, fine spatial features, such as the gaps between the wings, are faithfully reconstructed with high resolution. As is apparent from these results, having the area emitter is critical for high quality depth sensing. At the same time, the area emitter needs to have a spectrum that consists of two sharp peaks corresponding to the two optical wavelengths. Such an emitter is impossible to find in nature. As the area of an emitter increases, its spectrum also typically broadens. I'll give you an example. One of the sources that we considered using early on in the project is a sodium vapor lamp. That's of the kind that's used in streetlights. It emits two characteristic narrowly separated spectral lines and has an area emission profile, which apparently fits the description of the source that we want. However, due to the high pressures and the temperatures that are used in these lamps, the lines broaden and don't remain monochromatic enough for our model to hold. Therefore, there is a significant engineering effort involved in emulating such an emitter. Let's take a look at this. We combine light from the two single frequency fiber coupled lasers and collimate the output to form a parallel beam. Then we use a fast rotating mirror to redirect this light beam towards a lens that focuses the beam on its focal plane. As the mirror rotates, the focused point gets scanned along the focal plane to form our area emitter. As we mentioned before, other kinds of computational interferometry use area light sources with general spatial amplitude profiles. In order to create these profiles, we introduce an amplitude electro-optic modulator before the rotating mirror. As the rotating mirror scans the focused point, the amplitude modulator attenuates the beam in sync to create the required spatial profile. We then introduce the rest of the interferometer by placing this emulated area emitter in the focal plane of the collimating lens. Effectively, this mechanism time multiplexes the output of the laser in the focal plane of the collimating lens within exposure time of the camera. For general computational interferometry, we can replace the combination of the lasers by an appropriate light source and reintroduce the general reference arm configuration. Here is a picture of the optical setup that we built on an actively vibration isolated optical bench to implement direct-only synthetic wavelength interferometer. Remember the extreme sensitivity and high-frequency nature of interference speckle. Most of our design considerations make sure that the system is as stable and vibration-free as possible, while introducing the least amount of blur and distortion in the light waves involved. One of the benefits of this precise engineering effort is the robustness of the results to environmental conditions. As an example of robustness, we consider the performance of our setup under strong ambient light on the toy cup scene. Ambient light is a problem because it adds to the scene intensity image, but not to the interference, which results in a loss of SNR. Now, we flooded the scene with external light, such that the laser illumination consists of just 10% of the scene intensity at the camera. We see virtually no change in the reconstruction quality in the presence of background. We also have done experiments with 1% signal to background ratio and observed similar reconstructions using a narrowband spectral filter centered at the optical wavelength of the illumination. For more details, please check out our preprint called Swept Angle Synthetic Wavelength Interferometry, which is currently under review. Let us now talk about environmental conditions. Most current applications of interferometry are confined to the carefully controlled conditions of the lab because of its high sensitivity to environmental conditions such as noise, vibrations, and ambient light. For example, if we wanted to perform interferometry outside on a bright sunlit day using our own illumination, overcoming ambient light would require very power-hungry, high-intensity, and potentially eye-unsafe lasers. Therefore, ask the question, can interferometry be done outdoors with illumination from light sources like the sun that would traditionally be considered as noise? We call this approach passive interferometry because we don't inject any light into the scene and we use naturally available light instead. This is as easy as pointing our interferometer's input to the sun and using the incoming beam to perform interferometry. To assess the kind of interference signal that using sunlight would give us, let's examine the properties of sunlight. Since the sun is very distant, sunlight is nearly directional. In fact, sunlight is a collection of directional light waves propagating at a small range around half a degree of angle to its mean direction. As we saw before, this is equivalent to placing an area emitter in the focal plane of a lens. A result from Fourier optics called Fraunhofer diffraction formalizes this argument. In addition, sunlight has a broadband spectrum. Putting these properties together, interferometry with sunlight is equivalent to performing time-domain optical coherence tomography. This is a picture of the setup that we built on an ordinary utility card to test this idea out outdoors. It is obviously impractical to point the optical axis of the interferometer towards the sun, so we use a mirror to redirect sunlight into the interferometer. The entire of the optical setup in the white box is all imaging optics, and there is no light source in it anywhere. However, across an OCT scan, the movement of the sun in the sky poses a major problem. Therefore, it's important to track the sun and center it along the optical axis of our interferometer every so often. And we do that using a control system on the mirror that redirects light into the interferometer. Here's a video of the tracking in action across the entire OCT scan. As before, this optical setup required a considerable amount of engineering effort to get running. And here's a picture of me working very hard on this setup. Note that we are reliant on there being sunlight, and attempting this in Pittsburgh in the winter means spending a lot of time like this waiting for the sun to come out of the clouds. Nevertheless, we captured depth measurements outdoors. Here's a Google Maps shot of our experimental site. We performed experiments with our optical setup placed in the red box. We faced challenges including vibrations caused because of constant vehicle traffic, noise from the building transformer, airflow caused by wind and the building air outlet, and strong ambient sunlight with the occasional scattered clouds. Here are some depth sensing results captured using our setup and a 40 nanometer green spectral filter. Even in the face of the challenges that I mentioned above, we can sense micron-scale depth competitive to what we can sense in the lab for a variety of scenes with complex appearances, such as metallic, which is the coin, and translucent, which is the bar of Lindt chocolate. Let's take a closer look at one reconstruction result. This scene is a small part of a Raspberry Pi circuit board consisting of resistors, soldering pads, and conducting metal tracks. Here is a depth that's captured using sunlight interferometry, and the depth rendered as a surface and texture map. Let's take a look at two specific regions of the scene. One that consists of a soldering pad and a resistor in the green box, where we see that both of them are reconstructed accurately, and another consisting of a conducting track, where we see that the tracks are reconstructed with high spatial resolution in the texture mapped depth. Now that we have illumination that's equivalent to the one that's created by an area light emitter in the focal plane of the collimating lens, we can perform computational light transport in the same way as we did in general computational interferometry. Here's an example when we use the direct-only nature of sunlight to perform imaging through scattering. We image a French euro under three increasingly challenging conditions. 1, by itself. 2, with a ground glass diffuser pressed up against it. And 3, with the diffuser about half a centimeter away. Similar to the scene through scattering result before, even though images of the scene through the camera show blurred images, the interference component is able to recover a sharp image of the coin. For more details on this, please check out our preprint on sunlight interferometry on my webpage. In summary, we introduced a new framework of interferometric imaging called computational interferometry that allows precise micron-scale control on the set of light paths imaged by the camera in the scene of interest. We demonstrated two exciting special cases of computational interferometry, showcased a computational interferometric setup that's built on an ordinary utility card that enables passive time-of-flight imaging and seeing through scattering using only sunlight. We hope that the theory that we developed and the prototypes that we showcased will translate to future clinical and research applications in biomedical optical imaging, in addition to being applied to inspection and precision manufacturing. For me, my PhD life has been a learning experience on a human level as well. I find that the Grundfest lecture series, having this section where I speak about things that I wish I knew as a first year PhD student, quite unique and helpful for students who are just beginning their research careers. First, nothing in the world is worth compromising your health over. I know that people will tell you to take care of yourself over and over again, but I, speaking from personal experience, will pile on to that. You want the next best paper award at CVPR? Amazing. Go for it. Just don't forget about yourself in the process. A very important part of taking care of yourself is building a support system. I'm so very fortunate to have a bunch of people here in Pittsburgh that I can call family, and I seriously do not know where I would be without them. Talk to people, talk about research, talk about food, talk about random things. For research students, your advisor is part of your support system as well. The research that you do with your advisor, and it's not just a course, and your advisor is not just an instructor. Communicate, build a personal connection. They were once a student as well, and you will find that they understand you much better than you think they would. For this next part, I will quote a lot of The Importance of Stupidity in Scientific Research by Martin Schwartz. I highly recommend reading it if you haven't. It's very, very hard to do important research. The scope of things that we don't know, for all practical purposes, is infinite. Actively seek out opportunities to be productively wrong. In the process of correcting, you might just stumble across your next big idea. Schwartz says in the concluding paragraphs of his paper, the more comfortable we become with being stupid, the deeper we'll wade into the unknown and the more likely we are to make big discoveries. And finally, take lots of pictures. In the moments in my career when I felt frustrated or ready to give up, I found that these were a source of inspiration to go on. I built some seriously crazy contraptions in the course of my work, and I'm sure there will be points in your career when you'll also feel like this idea is crazy, let's try it out. Capture these moments, and at the very least, they'll be enough to put a smile on your face when you revisit them. Now that I have been looking for jobs and sometimes feel stuck or helpless in what to prepare, I look back at this picture of the time when I used to have a container of milk and a candle heating it on my setup. I think, wow, that was a really bad idea. And I can't help but feel lighted. With that, while I play a typical day in the lab for me, I can take some questions. Thanks for your attention.
Uh, Thank you so much, Alankar. That was really an awesome talk. Uh, we'll now take questions. So if anyone has questions, please feel free to raise your hand on Zoom, and we can go sequentially. So I think we already have some questions. So Angie, please feel free to go ahead and ask a question.
Oh, sorry, it's a clapping emoji.
Ah, I see.
Great work, Alankar.
Thank you.
Awesome. So while we wait for other questions, I guess Alankar, I have a few questions.
Yeah.
So you mentioned that like as especially very interested in your interferometric setup, the passive interferometric setup, because it seems something really that I've not seen before. So
Right.
you said you had to deal with a bunch of like noise, etc. So like, how did you resolve it? Like, is it just about like better isolators, or like was there something specific you had to do with respect to your setup?
Better isolation is definitely one of the things that we need to. Actually, you're stuck. Can other people hear me properly?
Yeah, we can hear you.
Okay, I think Pradyum disappeared.
Sorry, my net is a bit laggy today, but hi,
Okay.
can you hear me?
Yeah, I can.
Hi.
So better isolation is definitely part of the improvements that you make. One of the things that I think helped is the fact that sunlight, like interferometry with sunlight, has this direct only nature. And because of this direct only nature, it's much more robust to changes in to high frequency changes in global illumination than other kinds of interferometry would. So those are the two factors that I think we combined, and both of them resulted in these awesome results that we have been able to demonstrate.
That makes sense. Thank you. I think Rick has a question.
Yes. Hi, Alankar. Thank you for the talk.
Hey.
I really enjoyed it.
You.
Can you quickly explain, like, in an intuitive level, like why using an area light source can produce on direct only light? Is it similar to something like phaser imaging?
So okay, let me find the right slide for this. There you go. Okay, so there is a Fourier transform relationship between, like, you know that lenses do a Fourier transform, right? There is a Fourier transform relationship between the field that this generates and the wave field that's injected into the interferometer. And this tells us that like this Fourier transform relationship will tell you that the beam that comes out of here is spatially incoherent. Which means that there is no interference between, if I can get my laser pointer out here and out here. If you take this point onto the beam and you take this point onto the beam, and if you somehow redirect light from both of those into 1 pixel on the camera, they will not interfere. And as a result, any light that goes this way, goes into the scene, does some weird things, comes out here and goes in here, will not interact with any light that comes back from the reference mirror this way, right? Will not interfere. And effectively, any part of light transport that arises from illuminating any other point on the scene will get cancelled out in the interference. The only part that gets kept in the interference component is light that goes in, goes straight in, and comes straight out. Because that is the only part that can interfere with light at that point.
And in your implementations, I have a follow-up. So in your implementation, you use like a rapidly scanning mirror to create the area light source. That seems to like violate a bit on the area light source, right? So at every time instance, you only have one point that is lit, right? So does it means that like, so can you like give more detail?
Right. So the rotating mirror that we use is fast enough that this entire light source is imaged with happens with an exposure. So if you set your camera to infinity to effectively image the focal plane of the lens, you'll actually see an area light source at the right exposure. So what you do is you integrate the interference caused because of each of these points on the area light source, because that's essentially what the camera is doing, right? The camera is just integrating this across time.
But then does it still hold that if you're computing a Fourier transform using the lens to create spatially incoherent light, but your source field is not like coherent, like meaning because every time instance you only have one point that's lit, then does it still hold? Like
It does. That's essentially what we rely on. In fact, the fact that this point will not be illuminated when this point is illuminated makes sure that any light that goes out because of this point does not interfere with any light that goes out of this point. And that is very critical to us. The fact that we are able to create a spatially incoherent source here in the Fourier plane of the lens, in the focal plane of this lens, is critical in making this spatially incoherent as well.
Got it. Thank you.
Awesome. Do we have any other questions? Cool. So if not, then I think we can wrap up our lecture today. So please, let's give another great round of applause to Alankar for the amazing talk.
Thank you.
And yeah, thank you so much to everyone for joining in today. And thank you, Alankar, again. And yeah, bye-bye.
All right.